extraction of organic compounds. So organic chemists have to almost always do extractions from reactions. And it's basically you run a reaction and you have the molecule you want, your major products you want. And then you also have reagents that you were using in there maybe, or side products that you don't want. And so you can use the extraction technique to like extract out the major product you want and get rid of all the other stuff. And it's based on solubility. So it's like a perfect continuation from that solubility lab. So I try to make it fun, and I didn't do our students this year, but this was last year's class. So I have the idea of, like dissolves like. So I said, what if I have a bottle with a solution, a liquid of Bo dogs? Bo was in the class last year. He's got like the Snapchat filter face on there. So if I take a bottle of liquid Bo dogs and I pour it into a centrifuge tube like this, this is a centrifuge vial. And then I also add to that, after I've added the Bo dogs, I add some Omar cats. Does anybody know Bo or Omar from last year?
I know Bo from town.
Yeah. And then I squirt in some Omar cats. Will they dissolve in each other? Will they be miscible? Remember, miscibility means that they'll dissolve in any amount. Do you think the dogs and cats will dissolve in each other?
No.
No, because they're different. If they were similar, they would, but if they're different, they won't. So they make two layers. They're immiscible. So I've got the cat layer on top, the Omar cats, and then the Bo dogs down below. And who knew dogs were more dense than cats? I guess I was kind of thinking along the lines of domestic dogs tend to be bigger on average than domestic cats. But then in the wild, like tigers and lions are way bigger than wild dogs, right? But oh well, whatever. So in this case, the Bo dogs are more dense than the Omar cats. Okay, so now I'm going to take an Emily dog and I'm going to add her to the two layers that are immiscible. What layer do you think Emily dog will dissolve in more? Omar cats or Bo dogs?
The dogs.
Yeah, dogs, because like dissolves like, so it's a bit hard to see, but yep, she went down into the dog layer there. So if Emily was like my desired product of the reaction and I had some impurities, say I had some like little kitten impurities I didn't want, Emily would go into the dog layer with the Bo dogs, and then the impurities would be in the cat layers. And if I separate these two layers, I got my separated. Got a helicopter coming, of course. Try the headphones, not so loud. All right, so it's all like dissolves like again, but now with two layers. We won't have solutions of dogs and cats, which would be fun, but we'll have aqueous and organic solvents is what we'll use. And our aqueous solvent, water, it's very concentrated, right? We worked it out before. It's like 55 molar. Water, pure water is about 55 molar. And then we'll have things like dissolved in the water, sodium ions, hydronium hydroxide. And then our organic solvents, our most common ones would be like hexanes, very nonpolar, methylene chloride is nonpolar, and ether, aka diethyl ether. And they're not miscible in water. They'll form two layers. And you need that to do an extraction. You need an organic solvent that won't dissolve in water. So here's an example with organic molecules. Let's look at this here. So if I've got methylene chloride, it's an organic solvent, it's nonpolar. If you remember from the solubility rules, it seemed like it might be polar because the two chlorines and the two hydrogens and the tetrahedron, but it turns out it doesn't dissolve in water, so it's nonpolar. And then we have water, which is like our polar poster child, right? It's very polar. So do you expect these two solutions to form two layers or to mix together into a single layer?
Two layers?
Two layers.
Yeah. And then of the two layers, which layer do you think will be on top and which one do you think will be on the bottom?
Methylene chloride would be on the bottom.
Yeah, why is that?
Because it's
denser.
Yeah, it's like 1.33 grams per milliliter. Good job. Okay, and then if I took some of this naphthalene solid, naphthalene's it's what mothballs are made of. You may have like had mothballs I think, did Rob Tage, did you say you had mothballs in your closets? Some you could put in your closet to keep moths away from your clothes.
Yeah.
Was that last semester? Yeah. So it has a certain smell to it. It's a white solid. And so if I made a 2-layer mixture of the water and methylene chloride, there are 2 layers, and then I added some naphthalene solid, which layer do you think the naphthalene would dissolve in, the water or the methylene chloride?
The methylene chloride.
Yeah, because it's nonpolar. Methylene chloride is nonpolar, and the methylene chloride is on the bottom too, huh? That's unusual for an organic solvents. Most organic solvents, like Stephanie's question, most organic solvents are actually less dense than water, like hexanes and diethyl ether. So they wind up being on the top layer. So usually in extractions, your top layer is your organic layer, but not with methylene chloride. And methylene chloride is also interesting in that it's not flammable. It's like one of the, it's only one that can come off the top of my head I can think of, only organic solvent that's not flammable. Most organic solvents are very flammable, like hexanes and ether. Remember I did the ether trough demo where it burnt its way. The fumes are heavier than air. They tumbled down the rain gutter and then lit the candle lit them and they burnt up the thing. So very flammable. Hexanes and ether are very flammable. Pretty much all organic solvents are very flammable. Most of them are from the petroleum industry, like distilling crude oil, and they're components of gasoline, which is very flammable. Okay, and then naphthalene's nonpolar, so it winds up going to organic layer. Okay, so question number 1. In the figure above, I drew the reverse meniscus for the okay, so now I'm back at our Google Doc, and let's say we have benzoic acid and acetic acid, 2 carboxylic acids, and we want to separate them. They're both, well, acetic acid is a liquid, benzoic acid is a solid, but let's say you put some benzoic acid solid in the liquid acetic acid, and you're like, oh, I got to get these separated. I don't want them mixed up together. What you can do is you can put them in a centrifuge tube that has some water and an organic solvent. Let me see real quick, which one do I use? I use methylene chloride. So when I put the methylene chloride and the water in the centrifuge tube together, they'll form 2 layers. What will be the top layer and what will be the bottom layer?
Top would be the water.
Mm-hmm. Yeah, the methylene chloride is the more dense organic solvent, huh? Okay, and now the benzoic acid here, it's got this whole benzene ring that's nonpolar, and then it's got this carboxylic acid that's polar. Do you think it's going to be polar enough to want to dissolve mainly in water, or is it going to be more nonpolar and want to dissolve mainly in the methylene chloride?
Mostly non-polar. In methylene.
Yeah, if you,
chloride.
that's right. Yep. And if you remember back to the solubility lab when we had benzoic acid without any charge, just neutral benzoic acid, it wasn't soluble in water. It formed a precipitate. Okay, so now acetic acid, it's got the carboxylic acid area that's polar and just this little methyl that's nonpolar. Do you think it's going to be more water soluble or more organic soluble?
Water soluble.
Yeah, acetic acid's miscible in water. It'll dissolve in any concentration in water. So when I put these into the centrifuge tube, does this make sense? All right, good, thanks. Okay, so why is the methylene chloride on the bottom layer?
Because
It's denser than water.
Yep. Does the methylene chloride want to like avoid the polar glass and make a bulging upward like reverse meniscus?
Yes.
Yep.
yes,
And the water has a normal growing up the sides of the glass meniscus. Why is that?
it's polar. It's
Yep. And the glass is polar too, huh? And then the water actually grows down into the organic layer because it's polar. It likes the glass polar. Okay, and now why is my acetic acid in the upper aqueous layer?
because it's mostly polar.
Yep. And then why is the benzoic acid in the organic layer?
Because it's mostly non-polar and wants to avoid.
There we go. Yeah, I'm just kind of I know you guys got the concept, but I'm just really digging it down in deep. And so now after you have a situation like this, you can separate these two layers. Usually what you'll do is you'll put like a pipette into the lower layer and suck out the dissolved benzoic acid methylene chloride layer and put that in a separate flask, and then have the water acetic acid in this flask. And then once you've separated those two layers, you can let the solvents evaporate and you've got the two molecules separated. It's nice, right? So that's what this picture shows. So you could take a pasture pipette, suck out the bottom layer and put it in a separate flask, and then the aqueous layer will be left in the original.
Why don't you take at the top first?
It's interesting, Eligos. So see how the sides of this flask go narrow at the bottom of the centrifuge tube?
Mm-hmm.
So if I take out the top layer, it's kind of hard to just get the top layer because it's over a wide surface area right there, or a bigger surface area. But if I put my pipette through the top layer into the bottom layer, when I suck it out, see how it gets narrow? Can you imagine like my aqueous layer slowly coming down, and like I just have a little bit of a bead of organic. It's like much easier to just pull out the bottom layer that way. Does it kind of make sense?
Yeah.
Yeah, I'll show you in the lab video when I do it. So yeah, you usually will always draw out the bottom layer. All right. And so after we've separated the two layers, before you evaporate away the methylene chloride from the organic layer, this side over here, there'll be just a little bit of water still in here, because even though I pipetted up the bottom and I got mostly organic, there'll be like my pipette will pick up a little bit of water, and there's a tiny, tiny amount of water that dissolves in methylene chloride. They're not completely immiscible. There'll always be a little bit of water. So we need to dry what we call the trace amounts of water. Trace means just like a little bit in this organic layer. So that's that's like this standard extraction technique. You'll remove your organic layer, dry it with different techniques. So there's a couple ways you can do this. Yeah, there's two ways that we do this, and you don't always have to do both, but I'm going to teach you both, so I want you to understand both. So there's this thing called a brine wash. So brine is just saturated sodium chloride water. So to make brine, like organic chem lab brine, you just take water and you start adding salt, like table salt. And as you add the salt, it dissolves because it's very soluble in water. But after you keep adding salt, at some point it'll get to its saturation point and it won't dissolve the salt anymore. And you'll see undissolved salt in the bottom of the thing. Even if you stir it and have it like give it an hour of stirring, you still have undissolved salt. Then you know you have a saturated sodium chloride solution. And that's what we call brine. When we use brine, and I'll explain how it works, we take our organic layer and then we add brine to it, an aqueous solution of saturated sodium chloride. And then when we do that, we mix these two up and they'll form two layers, and then we pull the organic layer back away from the brine layer, and it winds up the organic layer is much drier than it was. It removes the bulk of the water, like 99% of the water, not all of it, but and it's a quick way to get almost all of your water out of your organic layer. So it has a high capacity. It can remove a lot of water. I think of it as like a pre-dry, like we're mostly drying it. Kind of like I like this analogy, like if you take a shower and you're gonna blow dry your hair, but first you use your towel to dry off most of the water. That's the brine wash. You use a towel to dry off most of your water, and then afterwards, if you want it really dry, you use a blow dryer maybe. And that blow dryer, the final dry would be this anhydrous sodium sulfate method. So sodium sulfate is a hygroscopic salt. Does anybody know what hygroscopic means?
Absorbs water from the environment it is in.
Yeah, that's right. Yeah, so if you take some sodium sulfate and you set it on the counter, even moisture in the air will start to stick to it. It can hold, I think it's usually like 6 or 10 water molecules per sodium sulfate. So this is really good at removing the last little traces of water. And almost all the water is removed by this. And but it can't remove as much water as brine, and so it's not as good at like. It can't get like if you have a lot of water in your organic layer, you definitely want to do a brine wash first to get most of it out, and then this just does the last little bit. So you can think of it as like the final dry. And the brine wash, the first initial, it's not always needed. So a lot of times, methylene chloride, if you didn't get any of your aqueous layer in there and there's only a small amount of dissolved water, you can just skip the brine step. But if you're using other organic solvents, like in the one above, the diethyl ether right here, diethyl ether dissolves more water in it than methylene chloride. So diethyl ether, you pretty much always do a brine wash, brine wash or pre-dry, and then you follow up with the sodium sulfate. All right. Okay, so here's a little bit more about sodium chloride. It'll dissolve in water to at 25 degrees Celsius, 357 milligrams per milliliter. That's a pretty good amount. And it's usually, stability does not increase. Doesn't increase that much with hotter temperature. Like we learned in this crystallization labs, when we heat up solvents, a lot of times things dissolve more. Some of them dissolve less, but most of the time dissolve more. I just thought it was an interesting fun fact. If you have pure water, sodium chloride is very soluble, but in concentrated hydrochloric acid, you don't, because the hydrochloric acid has all the chloride ions. So by Le Chatelier's principle, doesn't allow sodium chloride to dissolve as much. All right. So using the data above, here is the molarity of sodium chloride that's a saturated solution. Here's the, I don't have saturated. So 357 milligrams per milliliter of water when it's saturated, and 1 gram to 1,000 milliliters, and then I'll convert the grams to moles. That's the molar mass of sodium chloride. So it's about 6 molar, the sodium chloride saturated. And so you'll notice is that, the brine solution, when you have all that sodium chloride dissolved in the water, it's more dense than normal water, huh? But is it going to be more dense than methylene chloride brine?
No.
No, because brine, remember, methylene chloride still more dense, 1.23 grams. Maybe that'll be question 3, huh? Nice. Okay, so we know a bit about brine, but will this solution that is mostly water, so so brine here, it's mostly water still, huh? It's 55 molar water maybe, and 6 molar sodium chloride, 6 molar chloride. So this is still almost all water, and we're using it to dry an organic layer. That's kind of weird, huh? So you're telling me I can remove water from my organic layer using a solution that is mostly water? Do you guys remember the meme girl? Okay, so, well, it turns out that brine, mostly water, can remove water from the organic layer. And this is how it works. So, let me zoom in. So when you have your organic layer with your trace amounts of water in it, just a little bit of water dissolved in it, and some water that's not dissolved, you'll see like little beads of water in here. When you add your brine, it'll be on the top layer, and my meniscuses look good now, huh? Kids are having fun out there. So see how the sodium and chloride I'm showing, those would be in the aqueous layer. It's saturated, like 6 molar sodium, 6 molar chloride, 55 molar water. And the trace amounts of water, it'll get like drawn in, sucked into the aqueous layer, because the way I think of it as it's like an osmosis type of thing. Remember when you talked about osmosis in general chem, and they said, oh, if you have a semi-permeable membrane, the water will want to go through it to the side of higher concentration ions to dilute those ions. So the water wants to come out of the organic layer to dilute all this saturated sodium chloride. Also, you can think water's got a delta negative charge, and it's going to be attracted, and delta positive, so it's going to be attracted to chloride and sodium. So I like to think of brine as like water that's actually even more polar. It's not actually more polar, but it has all these extra charges on it, so it's going to draw water into it. Does that kind of seem like it makes sense to you?
Mhm.
Cool. And then after I've, added brine to my organic layer, and I actually shake it up and allow them to like really interact with each other. After I stop shaking them up, they separate back out. Then Elagosa, which one should I pipe off, the bottom layer or the top layer?
The bottom.
Yep. And then when I pipe it off the bottom layer, I put this bottom layer in a separate container. See how I went to like a rectangular test tube type of thing. And so my water sinks down and stays into the normal centrifuge tube. And now this guy went from having trace amounts of water to now I'm saying very trace. So I got rid of almost all the water. There's still some, but now there's a lot less. Maybe there was like 1% water in here, and now there's like 0.01% water. It's got like barely any water in it. And the brine is just slightly diluted. So maybe it's not totally saturated now because we added a little extra water. Okay, so. All right, so it's similar to osmosis, like I was saying before. You dilute the sodium chloride there. All right, so here's some brine pro tips. So how much volume of brine do you add, like if you're in lab? I usually use about the same volume. So if this was like, say, 5 milliliters of organic layer, I'll add about 5 milliliters of brine or less. It's not that big a deal. And then how many brine washes? Normally 1 is enough. But if you're like, if it looks like your organic layer is real cloudy, sometimes the water, the aqueous, the bits of aqueous layer that are dissolved in the organic layer, they make it a little cloudy. And when you add the brine, it helps clear it up. But if you're not seeing that clearing, then you can say, I'll try another brine. And then, when you're separating the layers, should you favor the organic or the aqueous layer? So what I'm saying is I'm going to do like Elagosa said. I'm going to put my pipette into the bottom layer and I'm going to suck it out. But as I'm sucking it out, I'll get to a point where there's just a little bit organic on the bottom and the rest of it's water. Should I try to get all that organic and in the process happen to get a little extra water into my organic layer? Or should I say, I'll just sacrifice a little organic in the bottom of it? What do you think is a better idea?
I think sacrifice a little.
You could, but in this case, I would actually not sacrifice it. The reason why is, let's say I grab a little bit and I pull a little of water into this. This will have a little more water and it'll grab some sodium and chloride. I'm not so worried about it because I'm going to do another drying later with sodium sulfate. I'm going to do a final dry,
Suppose like you get some of the brine in with your organic solution, wouldn't it leave some sodium and chloride like in that solution?
Yeah, good question. Yeah, and then in our next step, when we add the sodium sulfate, it's going to dry up that little bit of water, right? And when it does that, the sodium chloride that was in there, it won't have any water to dissolve in, so it just precipitates out. I'll show you. It'll make sense, Rob. That's a really good question. You're like a step ahead of where I'm going. That's good. So final dry, sodium sulfate. And the sodium chloride from the brine should precipitate with no water present. Yeah, just what your question was asking, Rob. So now for the final dry, we use anhydrous sodium sulfate. And so when we add the anhydrous sodium sulfate to our organic layer, that solid will drop down into our solution and fall to the bottom. But as it's falling through the solution, it'll grab onto these little bits of water that are still in there, the very trace amounts of water, and it'll form a hydrated salt. And I'll show you then what we do. Then we can decant away from that. Let me do it like that, this way. So I've got some sodium sulfate here. I've got very trace amounts of water. When I just scoop a little bit of that into my organic layer, and it's got no water. It's not hydrated right now. It's anhydrous. But as it comes through the solution, it picks up the water in the solution and it makes a sodium sulfate hexahydrate. It can make, I think, a decahydrate too, but I think maybe the I was looking forever. I think the hexahydrate's the most common to figure out how many, but whatever the case, it grabs onto water, right? And that sodium sulfate hexahydrate is a salt. It's not dissolved. It just falls to the bottom of the solution in the organic layer. So you'll see a visible solid in the bottom of the organic layer. And then you can decant away the organic layer from the hydrated salt. And to decant means you pour the liquid off carefully and leave the solid behind. Like you don't let the solid fall over into this flask. You just kind of gotta go slow. And then after you've done that, you'll have your last amount of water. And I didn't draw it here, Rob Tage, but at this point, when you added the sodium sulfate and it took away all the water from the organic, the sodium chloride that might have been in that water will be a solid too. So there'll be like solid sodium chloride in this too.
Okay.
And then we put it into our organic layer that's fully dried now. It's been pre-dried with brine, final dry with sodium sulfate. It's put into a beaker, not an Erlenmeyer. Why do you think I put it into a beaker? I want to evaporate away the methylene chloride. Do you think using a beaker is better or an Erlenmeyer flask is better?
The beaker better for surface area?
Yeah, it'll evaporate much quicker
Beaker.
from a beaker because it's got a lot of surface area. Yeah. If it was an Erlenmeyer that got to a small opening, it takes so much longer to evaporate. And then as I let it evaporate, when I'm done, I have benzoic acid by itself. Is anybody thinking to themselves, like, why do we make such a big deal about this trace amounts of water? Water is a liquid, it evaporates. Won't it just evaporate away like the methylene chloride? Is anybody thinking about that?
Lower evaporation point most of the time.
Yeah, the methylene chloride's boiling point is 40 degrees Celsius and water is like 100 degrees Celsius, right? So the methylene chloride will evaporate quickly. And if you want to warm it up, you could take this beaker and put it in a beaker of a slightly bigger beaker with warm tap water, put it in the fume hood, and it can evaporate like within minutes. Whereas if you have water in there as well, the methylene chloride evaporates, and then you have you have like a little bit of water with your organic solid. And a lot of times it's not only that water has 100 degrees Celsius boiling point, it takes a while, but sometimes the water will hydrate the organic things and they just kind of stick to it and it's hard to get rid of them. So it's much easier to get rid of the water from the organic layer than to try to evaporate it. There is cool special equipment to remove water from samples in different situations. They have these lyophilizers, they have these like centrifuges that are under vacuum and they freeze it and sublime it out. It's pretty interesting. But we usually just use the pre-dry brine, final dry sodium sulfate. So, okay, now, pro tip, how much sodium sulfate to add? So in lab, you wouldn't normally like weigh out a certain amount of sodium sulfate. You just kind of eyeball it. So as you're adding the sodium sulfate, and with experience, get good at this, you'll notice the solution starts to get clear, which shows you, oh yeah, it looks like there was dissolved water in there, now it's going away, the solution's getting clear. And also the first little bit of sodium chloride you add, when it forms the hydrate, it clumps together. So you can have little tiny grains of sodium sulfate that are anhydrous. When they get hydrated, they form like bigger grains, like clumpy, it looks clumpy. So as you're adding sodium sulfate, you'll see it clumps. It clumps because it's hydrating, clumps. And then when almost all the water is gone from the organic layer, you add sodium sulfate, it doesn't clump, it stays as little tiny grains. So that's pretty much how you know you've added enough. So it's because, for example, let's say Jesse had his organic layer and Elagosa had hers. Jesse might have more water in his. So I wouldn't say to Jesse, oh, everybody, and Jesse and Elagosa, okay, everybody add, 50 milligrams of sodium sulfate, because it depends on how much water you happen to get when you were doing your extraction. So maybe Jesse had a little more water in his, so he's just going to slowly add sodium sulfate, clumping. Oh, it's not clumping. I can see the grains. I've added enough. Where Elagosa was doing the same thing. She was adding, but she didn't have to add as much. It stopped clumping sooner. But either way, they're both dry. Okay, so that one's pretty obvious, right? All right, so now, why do we even brine dry, pre-dry? Why not just start with sodium sulfate since it works and it leaves your organic layer more dry? It's because if you have a fair amount of water in your organic layer, then you have to add a lot of sodium sulfate, and you wind up with so much sodium sulfate in your flask that when you decant away the liquid from the sodium sulfate hydrate, you have like a lot of your organic layers like coating all this solid surface area of hydrate. So you wind up not getting a good yield because it's just like, yeah, you could, but what you normally, you could get a good yield. You have to add a bunch more methylene chloride to your dry methylene chloride, fresh methylene chloride to your sodium sulfate hydrate, decant again, add some more, decant again. But then because of that, now you have a larger volume of methylene chloride you have to wait to evaporate. So, and you're using more chemicals. So it's better to do the pre-dry, but it just depends on the case too. Diethyl ether, you always want to do a brine wash, but with methylene chloride, oftentimes you don't because it's really dry to begin with. As I said, methylene chloride, or diethyl ether, we usually do a brine pre-dry to get rid of most of the water, and then a sodium sulfate final dry. So solubility in water. So you can dissolve 6 grams of diethyl ether in 100 milliliters of water. So it's actually pretty soluble in water, huh? 6% soluble. Whereas methylene chloride, you can only dissolve 0.02 grams in 100 milliliters of water. So it's like 0.02% soluble in water. So when we mix together water and ether, some of the water dissolves, some of the ether dissolves in water, and some of the water dissolves in the ether as well. I didn't have the data for the other way, but you can see there's water and ether are more similar. They dissolve a little bit in each other. And so the ether has a fair amount of water dissolved in it when you do an extraction. So you have to pre-dry and then final dry, where methylene chloride almost has no water in it. So you can just go right to the final dry a lot of times. So back up here. So let's say we add, we're adding our sodium sulfate slowly. It's clumping, making the hydrate. And then it stops clumping, you see little grains. You kind of shake it around and you're looking for little grains, not clumps. When you see that, you're like, great. So you decant it away, right? But when you do it, the sodium sulfate here, you'll probably have still a little bit of organic solvent in here with your dissolved product you want. There'll be a little bit left. So you'll just take fresh, clean methylene chloride, add it to this guy, and then recant again. Does that make sense? Kind of like washing it all over. Redecant, yeah. That's a funny word to say, huh? All right, and then the evaporation methods. There are many ways to do it. Some ways are faster, but you have to be there to do it. Other ways are a little bit slower, but then you can walk away and go do your dishes, work on another part of an experiment. So I generally have you do the a little bit slower walk away method. So that's the method where you you have it in a beaker. And then if you put this beaker in a slightly bigger beaker with warm water, but you set it up so that there's no way this could fall over in the beaker, the sizes of them, and the amount of water is not going to rise and spill in. And then the warm water will help this evaporate much quicker, because as the methylene chloride evaporates, it cools due to evaporative cooling. Do you guys know how evaporative cooling works? I was actually explaining that to Nick the other day for his 8th grade chemistry stuff. Can anybody explain evaporative cooling?
It takes energy to break bonds.
That's true. Yeah, intermolecular bonds too. So this methylene chloride, when it goes from a liquid phase to a gas phase, it's breaking the attraction between the methylene chloride molecules. And so it takes energy to take the liquid and break them apart from each other to become gas. It takes actually a fair amount of energy to do those phase changes. So as this methylene chloride evaporates, it gets cold. Actually, if you have a beaker of methylene chloride, it'll start to get frost on the outside if it's not in a warm water bath, because the outside of the glass will get cold, so cold due to the evaporation that moisture in the air can freeze on the outside of your flask. So if you want the evaporation to go quicker, you add warm water outside. It's combating the evaporative cooling. It's kind of like if any of you had gotten a little bit of acetone on your hand, or like ethanol or anything on your hand, and it feels really cold. Maybe has anybody ever used fingernail polish remover and it feels cold when it touches your skin?
Yeah.
Yeah.
Yeah. Yeah, so what that is fingernail polish remover. It's usually acetone and with other stuff, but so the acetone has a low boiling point. So when you put it on your skin, it evaporates quickly. And as it's going from that liquid to gas phase quickly, it's taking heat from your finger to do it. So that's why it feels cold. Also, like when you go swimming in the lake or something and you come out and you're in the air, you feel cold because the water is evaporating off your skin. It's taking heat from your body to evaporate. All right, so yeah, so that's method A, just that one. Method B, oh yeah. So we could do this same thing if we wanted to speed it up. If we're in a hurry, you can like blow nitrogen gas into this inner beaker, and it'll like all the vapor will be pushed away sooner, and it'll evaporate quicker. Or you can use a blow dryer, because that will. But you don't want to use a blow dryer if your stuff inside of here is like could be oxidized easily, because then you're adding heat and oxygen from the air when you blow at it. Nitrogen is the safest way because nitrogen's unreactive, so your molecules in there are being surrounded by nitrogen. Oxygens get pushed away from it. Okay. And then we have a thing called a rotary evaporator. I think I might have video of that for an experiment I'm going to share with you later. I think I do. Total synthesis. I'll have to look. But rotary evaporator is pretty cool. I'll show you that later. It's a way to evaporate solvent quickly. And it's if you have a large amount of solvent, like instead of like it's not like 10, 15 milliliters, but more like 50 to 100 milliliters of solvent, rotary evaporators are great because you can just set it on there to get started and it evaporates quickly and you can walk away. It just does it for you. Yeah, and you notice above, I said we're going to evaporate the organic layer, and we don't usually tend to evaporate the organic layer. I mean the aqueous layer, because the aqueous layer has a high boiling point, 100 degrees Celsius, where N-hexane is pretty low, and then methylene chloride, diethylene is really low. It evaporates quickly. Okay, now here we go. Yeah, some acid-based stuff. So this is one of the biggest concepts we're going to use for extractions, and I already taught you it in the solubility lab, because it's one of the main things in lab we learn about, is that if you have a neutral organic molecule, like this guy right here, this carboxylic acid, it has no charge. Is it more soluble or less soluble than its conjugates with the negative charge in water?
Less soluble.
This is less soluble in water. With the negative charge, it becomes like much more soluble. And so when we have a carboxylic acid, the sodium hydroxide is great at deprotonating it, right? Because the pKa acid is about 5, 16, very product favorite, 10 to the 11. So if you ever have a carboxylic acid that, say, is in an organic layer, and you're like, oh, I want to get that into the aqueous layer, you can deprotonate it, and then it'll go into the organic layer. And let's say you have it in your organic layer, and you separate out the organic layer. Then, I mean, you have it in your aqueous layer, sorry, and you separate out your aqueous layer. Then you could add hydronium, an acid, like acidic aqueous solution, and you could protonate it back and make it organic again and make it go back into the organic layer. And this is very favorable as well, 10 to the 7. So there's 4 big reactions. I mentioned that in the solubility. Here's the 2. So acetic acid, or not acetic, carboxylate, I'm sorry, carboxylic acid to a carboxylate, and then a carboxylate back to a carboxylic acid. And then the other one is an amine to an ammonium, and then an ammonium back to an amine. So here's like the summary here. Acetic acid is neutral, right? And it's much less water soluble when it's neutral. It's more organic soluble at this point. If I add sodium hydroxide to it, it'll be deprotonated. Now it has charge. It's way more water soluble and not as organic soluble. If I have this in, say, my aqueous layer and I want to get it back into the organic layer, I can add acid and boom, it goes back to here. Now it's more organic. You send it back and forth between the layers. And you do the same thing with amines, but it's interesting that the amine, when it's neutral, it's organic soluble, less aqueous, but you add acid to make it aqueous soluble, or with the acid, you added base to make it aqueous soluble. It just has to do with charge, no charge, right? Okay. So let me actually go to this. Animations. Solubility lab, huh? There it is. The big four. Boom. Oh, I got the whole Four Horsemen reference here. All right, so this guy right here, does it look more organic soluble or more aqueous soluble? What are you gonna guess? Is it gonna be more soluble in an organic like methylene chloride layer or more in the aqueous layer?
Organic.
And
Yeah, it's got a lot of organic, huh? Just that little bit. So I think this, if I have an aqueous and an organic layer, 2 layers, it's gonna be in the organic layer. And then if I take and I add hydroxide to it, what's gonna happen?
Deprotonated.
Yep. And when it gets deprotonated, it becomes negatively charged. So is it now just as organic soluble, or is it less organic soluble and more organic aqueous soluble?
More aqueous soluble.
Yeah, and this guy will pretty much just, all of it will mostly go into the aqueous layer then. So when I have those 2 layers, I add some base, deprotonate all the acid, shake it up, and it goes into the aqueous organic layer. It's pretty cool. You can switch it into the aqueous layer. Sorry. Okay, so now let's look at another one. What if I have this other molecule? It's got a lot of organic, huh, but a negative charge. What do you guess? It's going to be more aqueous soluble or more organic soluble?
Aqueous.
aqueous.
Yeah, it's more aqueous soluble. If I add hydronium, though, it'll get protonated, product favored reaction. And now what is it?
Organic.
Organic soluble, so it'll go into the organic layer. Nice, right? What about this guy? What do you think he is, this ammonium? Do you think he's got a lot of organic there, but he's got a positive charge? Do you think he's more organic or aqueous soluble?
Aqueous.
Aqueous.
There we go. And then what do I add to make it more organic soluble?
The hydroxide.
Yep. That's it. And now it's more organic soluble, right?
I have a quick question.
Yeah.
For the one that's aqueous soluble, the last one you did, well, I thought that would be organic because of the positive charge.
Oh no, remember whether it's negative charged or positive charge, any charge makes it more water soluble. The reason
okay.
why is, do you see how the water molecule, it has like a delta minus end oxygen and then delta
Yeah.
positive hydrogens? For example, this one, Exnosa, is what part of the molecule, water molecule, is going to be attracted to the negative charge, the oxygen or the hydrogens?
The hydrogen.
Yeah. And then what about for the ammonium? What part of the water molecule is attracted to it, the oxygen or the hydrogens?
The oxygen.
Yeah. So water's got, it's polar, it's got 2 ends. So water just likes any charge. I'll take positive, I'll take negative. Water doesn't like no charge.
Okay.
Yeah, good question. A lot of people mix that up at first. So I'm glad you asked. And then this guy, what do you guys guess? Organic soluble or aqueous soluble?
Organic.
Yep, because no charge. And then I give it hydronium, gets protonated, and now it's aqueous soluble. You got it, right? I'll make a question up where I have you guys fill this out again, this kind of thing. When we have 2 layers, oh, Demonpreet, did I do it right with the aqueous meniscus?
Yes.
Yes. Okay, I meant to say rotate. So when I have an aqueous and an organic layer, they can only react with their surface. So like this hydroxide that's up at the top of the aqueous layer, it can't touch this water, this benzoic acid in the organic layer because it's too far away, right? They have to run into each other to deprotonate. So like these hydroxides up here, they can't react with these 3 acids down below, huh? only at the surface can you react. The hydroxide can react. This hydroxide can react with that acid because they're right at the surface, right? So this isn't really a great reaction condition, is it? Because we don't have a homogeneous solution where everything's dissolved together.
Should we mix it?
We mix it, we shake it up. Shake, 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 boot it. Yeah, we shake up the 2 layers. And when they shake up, they make little beads of water in the organic layer and little beads of organic in the aqueous layer. And I'll show you in the video when I'm in lab. So you shake it up and you'll see the little beads. You've seen it probably before. Have you guys shaken like salad dressing, like that's separated? Like oil and vinegar salad dressing?
Mhm.
Have you ever seen that? Where you shake it up and it makes little beads and then they separate back out, right? When I worked at a grocery store, we'd do little pranks with new people. We'd tell them like, oh, we're gonna get inspected. You have to go shake up all the salad dressings. They will need to be mixed before they come to inspectors. Or you tell them like, oh, we need to go mop the freezer because if when you put the mop on the freezer floor, it like sticks and freezes on it. So anyways, when we do this, does this help our reaction?
Mhm.
Yes. Increase.
Yeah, because for instance, the water is blue. This little droplet of water has hydroxide in it, and the orange organic would have the acid. So now all the surface area around that droplet can react. So you have a lot more surface area. So usually for these kind of things, you'll shake it a lot, let it separate out, do an extraction, and then you probably will do more than one sodium hydroxide wash in this case, because your reaction conditions aren't that great. You got to kind of just overdo it.